Okay, let's see here. We're going to pick up where we last left off, last lecture. So let's see. We started the bomb lab, right? Was everyone able to successfully make their own bomb? Now, there's been some technical difficulty with the bomb platform delivery service. As you might be aware, it's not an extraordinarily secure service. It's prone to failures at every so often. So if for any reason it goes down, let me know. Like earlier, I went to go set up for it and it was down. And so I had David relaunch it. So he had just recently rebuilt that VM. So if we have any issues, let me know so we can go ahead and get that relaunched. But it should be functional now. I think we last left off in a prior class motivating the concept about bomb lab, what it was, how to get a bomb, and how to use strings to go ahead and find what the key word was for the first bomb. Now I'm going to show you a second approach for that same phase. The first phase used the strings app. The second phase will use the actual debugger, and we will kind of learn to use the debugger more in line so that we'll be very reliant on it in the latter phases. We're going to probably see two different ways to do phase two, and then once we get to phase three, we're going to definitely need the debugger to move beyond that. So to kind of ease us into phase one with the bomb, let me open up my terminal. Let me go here. I'm going to disassemble. I'm going to start evaluating the bomb that I used actually last semester so that my slides are congruent, so I don't have to remake all my slides. So let me go ahead and open my terminal here. Let me go and just make sure I'm inside my terminal. Let's change into my bomb. Perfect. Okay, so now I can see I'm inside my terminal that has all of my bomb paraphernalia in there. Okay, so the first thing we want to do is we want to launch our debugger. We saw how we can do that. We're going to use the new debugger, GDB. And then we're going to pass the application we want to debug. As we stated earlier, Dr. Evil was very kind to compile his application with the to be very verbose and not to destructively destroy all of the function names. It makes reverse engineering his code much easier. So let's go ahead and put our bomb in there. Okay, so at this point, we've launched our debugger. Now we are inside the applications with the various options that we have. Let me make sure there's no comments there. Okay, so at this point, we saw how we can run. So I'm going to start off from where we last left off. I can run, and this runs the application. At this point, I can kind of key in words. Here, I'm just going to do Control Q, though, because I don't want to pass in any words at this point, because we want to actually set up some safety nets. So we are not going to there we go. Now let's quit out of there. Q to quit, and then I'll clear my terminal. Okay, let's do this again. But instead of just running the application, let's set breakpoints. Breakpoints allows us to stop our code at certain specific labels or memory addresses. So we're going to launch that. At this point, before I run my application, this is the point where I can do all of my preliminary setup for how I want to investigate my running application. So I'm going to set a breakpoint for explode bomb. And notice now we have our first breakpoint set at a particular memory address. That memory address is where the label of our function explode bomb is at. In fact, to illustrate, what if I try to set a breakpoint with a label that does not exist? Suppose I put explode bomb, small typo. Well, that's perfect. It's going to say not defined. Okay, so at this point, if I go to run my code, so I launched into my application, and if I go and type just any random string in there, normally, if I was running this outside the debugger, this would lead to an explosion. Now, what it does is it still leads to the explode bomb function call. We can see this right here because that's what gets invoked, but that's also when my breakpoint triggers. So long as I set my breakpoint to catch that label, I'll never, unless I'm not paying attention, I shouldn't explode my bomb. I could still explode the bomb if I put in, like, say, for instance, continue. Ignore that, just continue. Well, now what I've done is the bomb is blown up. So keep that in mind. Even with the breakpoint set, it'll stop you, but you can override the stop and just continue. And this is easy when you're like investigating the registers and you get into the flow of doing things and you're like, you don't pay attention for one small brief moment, then suddenly you've exploded the bomb. Okay, let's quit out of this. Okay, so now that we've seen how to set a breakpoint, let's see how we can not only prevent it from exploding our bomb prematurely, so that if that were to happen, we can back out, but also how we can start investigating the code that's running in our system so that we can use that to effectively reverse engineer the strings we need to be able to disarm this bomb. Okay, so again, let me do my DBG. Let me go into my bomb. Perfect. Oh, wait. Oh, sorry, GDB. Okay, and now let's set a break for my explode bomb. Perfect. Let's set a break. Now, if you remember, we did a large evaluation of the code that was given to us inside of the bomb.c file. And some of the function calls that are very interesting was phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. So presumably, let's pretend we don't already know what the phase 1 passcode is. Then I can set a breakpoint for that function too. Phase 1, there we go. We now have 2 breakpoints set up. And so if I go and now run my code or run the application, not my code, Dr. Evil's code. And then what I can do here is, let's say I type in hello world and give it some prompt. I'm going to hit enter. And now the first thing that's going to trigger is my phase 2, because that's the thing that's going to evaluate to see if my user input matches what's expected before it makes the decision whether it's going to explode the bomb or not. Okay, so now there's some interesting things we can look at. If I look at the very bottom here, it shows me where I'm at. I'm at breakpoint 2. It gives me the memory address at which this function is at, and it gives me the label if there's a label attached to this memory address. Then we can see my program stack, my application stack here, right? My call stack. So I started at the main function, and then the main function invoked phase 1, and phase 1 is the function I'm currently in. So this gives me a trace of where I'm at in the application, a historical trace. Now, the next thing I'm going to look at here is we have all of our, right here, this green with the arrow is the location of the instruction that I'm at when I first launch into my phase 1 function, my C function. Now, recall that when my C function initially calls, it does all sorts of preambly things. So there's like a prologue where it goes ahead and pushes things onto the stack. It pushes the any kind of callee functions in if necessary, and then it has an epilogue phase. We'll look more of that at phase 2. But at this instance, the things I'm interested in is, well, let's see what's happening here. So I am, yeah, this is some preliminary stuff. That's like general pattern stuff that machine-generated assembly is going to embed. The thing that's interesting to me is this line here, right? So here we're moving from our extended source index. Now recall that's usually a parameter that comes from a function, some register space. So we're moving something into ESI, and now we're calling this other function, this external function, by this memory address that's called strings not equal. So I'm assuming that the evaluation of phase one is probably happening at this line here. And let's see what happens. Then it's going to test whatever's in EAX, and then it's going to jump if it's equal to this memory address, and this memory address, notice, so these jumps is at would be after this memory address here. So, and then this is a call to the bomb. So what we can see is we're going to check to see if it's not equal. We'll evaluate that, and then we're going to jump. And if it's not equal, we're going to explode the bomb. If it is equal, then we will be able to move on to the next phase. So can everyone kind of see what's happening in this assembly enough to be able to understand? So let's what would be nice is if we could see what's happening in the register space at this particular call here. And we can do that, actually. We can go to each next instruction. So we're currently at this instruction, not an interesting one. So next I brings me to the next instruction. And if you see now, my green arrow with the line that I'm currently at has now advanced to the next instruction where I'm moving a value into ESI. And so let's call that one more time because I want to get to this instruction where I'm calling strings not equal. Now at this point, let me see if, so at this point we've moved something into, okay, so there I'm inside of strings not equal. I've moved something into RSI previously. So let's actually use the ability to look at the hexadecimal values of what's inside of RSI. So I'm going to use X to get a hexadecimal value. And then I want to be able to get, I want to read the value from a register space. So I'm going to do X/S. And then to read a register, I'm going to use the $sign. And then it's RSI that a value has been moved into. So I'm going to see what that value is. Now, for this particular bomb, the thing I'm comparing against is the statement that we need to actually supply. So it's going to be proton guns are well and good, but sometimes you need the Swiss Army. So what I can do here is I could copy that. And now I would hit continue. And now, since I typed in hello world and not that phrase, it's going to bring me to the explode bomb. At this point, I'd want to quit out. Now, if I wanted to test that, I could just launch the application and play really dangerously. I'm not going to do that. I'm going to go ahead and use our debugger again. Going to set that up to launch our bomb application. I'm going to always make sure that I set my breakpoint for my, and I'm going to do this manually each time so you get used to seeing this. Gonna set my explode bomb just in case, but at this point, I'm not going to debug anymore. I'm just going to go ahead and run, and I'm going to test that out. So I'm going to paste in here. Oh no. Probably don't want these strings. So let's actually, well, paste. Okay. So go into explode bomb because we have quotations. So clearly we don't necessarily want the quotations into what we have. So let's do this. Let's quit. Let's echo. Paste. Grab what we just want here. Copy that. Okay, now let's go back into our bomb. Let's set our breakpoint. And let's run. And let's try that again. Paste that. and phase one diffused. So now you've seen two possible ways for us to go ahead and diffuse the first phase. The first, we use the strings application, and the second approach, we use the debugger application. Does anyone have any questions about how we were able to accomplish that? What was your question? Oh, echo is a shell command that will print out whatever I send to it. So just to give you an idea, let me quit out of this. Yeah, there's all these fun little shell applications that are good to kind of learn. So here we have echo, and then I'll type in hello world, and then it just prints out hello world. Now you might wonder, why would I ever use echo? So some common rationales on why I use echo every so often, just to give you some, I guess, a daily hack trick, is whenever I launch a new GitHub repo, one of the first things I always need to do is create a .ignore file and put .ds stores in there if you have a Mac. How many people have Macs, just out of curiosity? Yeah, so one person at least shares this pain. One of the unfortunate things about Macs is they put a hidden file into every directory in order to track what files are in each folder. And that's your .ds store file, which means they automatically get added into your Git repo, which is just garbage files. Like, those are not things that you should be sharing. That's for your, and this is true for things that aren't just related to Macs. There are sometimes private files that are in the repo for your own testability that you don't want to be part of the public repo. That might be other things like API keys or anything that's not public knowledge for the application, or things that are just local to your machine, or anything that are like dependencies, because a lot of times each machine should build its own dependencies for an application. So has everyone built a .git ignore file before for your repo? Is that at least something you've seen before? So instead of launching a text editor where I create a .git ignore file and then just putting .ds store, one thing you can do is just do echo, and then you can put .ds store. That's supposed to be a dot. And then you can do a redirect. So instead of standard output that you're printing this text to, you can send it to a file, say for instance, a .ignore file. And then all of a sudden, I should now be able to look at my git ignore file, and you can see I already have a .ds store. Oh, I think there's an underscore in there as well. It doesn't matter. The proof of concept is still the same. That allows me to very quickly print things from instead of to my output stream to a file stream without having to launch big applications, right? This very lightweight application that does a very simple task that doesn't interrupt my workflow. And that's what these small little shell applications are really good at. Like, for instance, if I want to remove quotation marks. Good question. And this is what's really going to make me look forward to all the group presentations that y'all are going to show off, to be able to highlight all the very valuable and popular and useful shell applications that are available that'll make you much more proficient, not just understanding how the shell works, but actually being able to use it as part of your workflow for developing software. Okay.
I have a question about one of the steps you did. You did the x/s and then the $RSI, and that'd be something that we should know. It'd be like somewhere we could like look to figure out how to look at your.
That's a great question. So we're going to look at that more and on phase 2 as well. So x allows me to be able to print a hexadecimal value, hence the term x. Then the slash and the value after that is going to effectively be the amount of memory I want to access to be able to build that hexadecimal value. If you want to read more about the actual parameters, because remember, we've transitioned now where I'm just kind of showing you this very narrow way, you'd want to either look at the man pages on the new debugger, or you can go ahead and use the help command on new debugger. So as I start to step through all these concepts, and you're seeing some of these new commands you haven't seen before, I'm now offloading the work of broadening your understanding to you to go read the APIs. But two places to go look. There are man pages that are available. That's like your API documentation that you can launch right from your shell using the command man, short for manual. And also the debugger itself is an application that has a help option. And the help option will allow you to go ahead and ask about any particular thing. Good question, though. And we'll look more at that particular command as we go further along inside of this lab. Okay, is there any other questions in terms of at least phase one? Okay, let's go into phase two. Now we're gonna look at phase two in one of two ways. There's actually two ways to solve phase two, just like there's two ways to solve phase one. In fact, I'd argue there's probably more than two ways. There's only two ways that I'm gonna cover. So I want to take an analytical approach at solving phase two, and then I want to take an exploratory approach at solving phase two. So one that's going to be heavily reliant on using the debugger. That's going to allow us to explore our memory space, our register space, what's happening at each line as we go ahead and execute it, and kind of feel out what's happening in the application step by step. And then another approach, I want to use object dump, an application we've seen before, just to be able to get access to the disassembled assembly code and try to reconstruct what's happening inside of phase two, which is going to be the analytical approach. That's what I mean to distinguish between the exploratory and analytical approaches. Okay, so I'm going to start with the object dump approach. So let's start with these. So let's do, okay, make sure I'm where I'm at. Yeah, perfect. Make sure there's no comments here. Yeah, perfect. So I'm going to do object dump. This is an application we've used before and we've lectured about multiple times. Let me also stretch my window out here. Okay. And then the next thing I'm going to do is I'm going to put my flag. Come on. Don't lag on me, computer. I've gotten an unstable connection. The only problem with doing these labs, depending on the VM, is sometimes it connects and can go unstable, and then you got to take a pause. Okay, so I'm going to object dump, and I'm going to use that -D, and then we're going to do the bomb application. And instead of printing this out to the console, I'm going to redirect this to a file that I'll call bomb.s. Perfect. So that allows me to open it up and explore. I can do cat. Cat allows me to inspect the contents of a file right from my terminal. So let's do that initially. So bomb.s, we can then see that, oh, I have all sorts of columns. Okay, so this is a really hefty file. It's going to be kind of burdensome for me to investigate it inside my terminal. I could use a text editor inside my terminal to do that. I'm just going to use whatever's built into our window display here. So let me just grab this. I'm going to double click it. Okay, so here, one of the great things that is to our advantage is we can actually see now what our disassembled code looks like. It gives us the opportunity to peer into how this application is constructed. Now, what you should notice is that we have the labels for each of our functions. So this first column, as we stated in lecture, is our set of memory addresses. So if you see, this is our memory address, and starting from here, you can see it increments for each set of hexadecimal values that encode the set of instructions that this procedure executes. So this is the set of memory addresses. Inside this memory addresses is the hexadecimal representation of our application logic. And then this third and final column is going to be the retranslated assembly instructions. Okay. And of course, it jumped us right to where we want it to be. Phase 2. That's the interesting function for us at this moment. But if I were to scroll up or down, you can see that it would have more of these functions that we care about. But let me go back to where, yeah, like for instance, we have the logic for phase 5 here, but let's go back to phase 2. That's the one that we're trying to solve at this moment. Okay, so the first thing we see is we're doing some pushing here. Again, that's going to be preliminary prologue stuff before our core body logic can execute the machine generated assembly code is going to have patterns that are for system level management between transitioning from one function call to another function call. So we can see we're pushing some register spaces onto the stack. And notice when we're done, we're popping those back off. We're returning those, right? So when you start to learn how to read machine generated assembly, you start to see what these kind of prologue and epilogue calls are that help set up the stage for a function to start executing and then breaks it back down so that we can return to the callee function. We can see here, okay, so we have here, we can see we're moving our stack pointer, right? So we're making room on our stack pointer. Then we're taking our RSI and we're moving that in, and then we're calling this function here. Oh, that's an interesting function. Read 6 numbers. That's a bit of a clue on probably what the input is that we want, right? Let's see what else we have here. Then we're going to do a comparison to the value. Now remember, when we're put things in a parentheses, we're effectively doing like a dereference of a value at the stack pointer, and we're comparing it here. And then right here, we're going to, and right here, we have a call to explode bomb. So this looks like a pretty vital comparison. And then we're going to do a jump based off of that comparison. And depending on what happens with that jump is going to depend on whether we're going to explode the bomb or not. Okay, let's actually jump. In this instance, I have kind of paired the assembly with some comments so that you can actually read my comments, so you don't have to follow my voice and kind of memorize what each of these statements do. So let's actually jump to that. Okay, so we already said that the structure of our object dump is going to give us the addresses, the machine code, and the assembly code. And again, everything is going to be in little endian format, which we've established earlier. So the first thing we do is we recognize those common function prologues. That was this push RBP, RBX. It was the subtraction from our stack pointer by this amount. So effectively what we're doing is we're saving our old base pointer. We're going to save our old BX register. And these are both callee saved registers. Then we're going to allocate some stack space for the local variables and save registers that's coming in from our function call. And then what we're going to do is we're going to typically use to prepare for our next operation, we're going to move our source index into our stack pointer. And then we have our function body. That's going to be the actual logic we care about. So this is going to be pretty common in most functions. And then at the end, in the epilogue where we do our breakdowns, the kind of common pattern you're going to see is we're going to deallocate that stack space that we allocated before we started doing anything. We're going to pop those registers back off, and then we're going to return back to our called function. So this stuff we can kind of ignore when we do our initial inspection. Okay, So then with that said, let's take a look at what our reading 6 numbers looks like, at least from the debugger's perspective. So here, all I did was I grabbed that sequence from our object dump and pasted it in here. And then I went ahead and I provided our comments to each side here. So in our first line, you could see when we call this read 6 numbers, we're going to allocate 24 bytes of stack space because this is a hexadecimal value here. Then we're going to load the effective address of our second number into RCX, that's our counter register. Then we're going to load the effective address of our 6 number into RAX. So notice we're indexing into our source index, and then we're going to be offsetting by 4-byte increments. Then here, we're going to store the address of the 6 number onto the stack. We're going to load the effective address of the 5th number into RAX. And then we're going to load the effective address of the 4th number into R9, load the effective address of the 3rd number into RDX. So effectively, you can see we're moving the values that are passed to us into our register space. Then finally, we're going to initialize EX to 0. This is the scanner's return value, which would be stored here. And then we're going to call scanf to read 6 numbers. And then we're going to return the value of scanf with 5. And if it's more than 5 numbers, we jump to address number 61 here, which would be where we return from this function call. If it's 5 or fewer, then we explode the bomb. So effectively, what we can see that our read 6 numbers is doing is it's a helper function inside of our bomb application that checks to make sure we have 6 values. And if we don't, it explodes the bomb. So no, you can explode the bomb in helper functions. But we can, if you're doing, let me restate, we're doing an analytical approach. So we can see that by looking at each of the functions that's called. The first one we looked at was phase 2, and then we started to look at what was happening in each line of assembly and see what comparisons lead to a jump that effectively lead to a explode bomb operation. And when we first saw that there was a helper function read 6 numbers, we found that inside of our object dump, and we broke that down. And the big interesting thing here is it's ensuring that our input then has to be 6 numbers long. And if it's not, we'll explode. And actually, let's see here. Let's see if, well, no. We're going to play around in the Explorer. Don't want to mix and match. Thinking about running into the debugger, we will wait for that. Okay, so let's jump back into our phase 2 code. Now that we kind of have a slight understanding about what read 6 numbers does, even though I think the name of it was pretty spot on. So here, what's in the red was all my preambly stuff, right? Here and here is all the stuff that is not really part of the core logic of the function. Now, where it gets interesting is where we go ahead and call this. So here is when we're calling that helper function to read those 6 numbers. At this point, our registers should then be loaded with the 6 numbers that we had passed in to the application. So then the next line after we do that is going to be a comparison. We're going to compare the value at the stack pointer addressed to 0, right? So again, our stack pointer, we're dereferencing when we put the parentheses around it, and we're comparing it to the value 0, and we're going to jump if not negative. So if it's positive, and we're going to jump to this address. And notice I've highlighted the addresses for ease of readability to be this blue color. So this address is what? 4010SF. That's going to be this address here, right? Am I? Yep, that looks correct. So we would jump here. Which is, if you look, advances us past the explode bomb. So what that tells us is if our number is negative, we explode. So non-negative numbers. We got a hint already. Okay, the next thing we're going to do is we're going to move the stack pointer value to the base pointer. Now, we can kind of think of our numbers as being stored in a contiguous block of memory, so we can be able to index to access them. So the next thing I'm going to do is I'm going to load the effective address of my whatever reference I have in my base. And that's inside of my RBX register space. So I'm going to load the value there. But when I load the effective memory, remember that if I have this value on the outside there, that constant value, I'm doing an increment on it. This is a very cost-effective, performance-wise way of doing an increment. So I'm incrementing the value of RBX by 1. You can see that in my comment here. And then I'm going to load that into my EAX register. So I'm taking RBX, increment it, and putting it into EAX. Then inside this line here, I'm going to add the value at the address that's calculated by my base pointer, offset by RBX. So RBX is my offset into my array. And then since these are integer values, they are 4 bytes large. So I need to have a 4-byte offset. And then I'm going to add that with what's in EAX. So this gives me a really good clue as to what I'm looking for to inspect for my input. Then, and the reason why is I'm going to do a comparison with that. I'm going to then compare EAX with the value that's inside of that base pointer, offset by that index, which is my RBX, in 4 block elements. And notice this is doing, you have this value here. That's the equivalent of effectively advancing by 4 memory addresses. So if you think about this as an integer array, it's like peering into the next element of the array as opposed to one I'm currently at. Does everyone kind of see that? Right here. This. So if this is grabbing the current element in the array, this is like grabbing the next element in the array. Because that 4, that hexadecimal 4 value that's on the outside of the parentheses is advancing our memory location by 4 bytes. So it allows me to offset my memory location. Now, this is my comparison. The comparisons are always what's key with being able to solve what's happening with my bomb logic, because that primes all my registers to then do a jump. Here I'm going to jump if equal. So if my EAX value is equal to whatever the value in the next element of the array is. So if it is, I'm going to jump to this memory address, 401099, which is going to be here. And look at what I jumped past then. There's only one statement between those two. It's an explode bomb function call. So this allows me to avoid exploding the bomb. Then after I do that, I'm going to compare my BX register to 5. And if it's not equal, I'm going to jump to memory address 401087, which is up here. I'm jumping backwards because this is a loop structure, which you should already be familiar with assembly. That's why we kind of skipped it inside of our earlier lectures, is that all the logic stuff you should be familiar with labels. Or I guess we're not using labels, but you know, memory addresses, numerical, these are just numerical labels, right? So clearly, this right here is going to be my loop logic and my loop condition, such that once I get to effectively index 5, once I've done this for all 6 of my digits, I'm done. Which means I would then break out the loop. And when I break out my loop, well, that's all the stuff that is my epilogue. That's the deconstruction of this function. And then I return back. And we know after inspecting our main function last class that if we can get past phase 2, we'll go to the diffuse bomb function call. And then we made it through this particular concept. Okay. Or this particular phase, not concept, but phase. Okay. So does this kind of walkthrough of the assembly kind of make sense for my bomb? Remember, you have to understand what's happening here because your bomb's going to be different. You can't simply use the same inputs. But notice how I was able to go ahead and identify each of these lines in an analytical approach, evaluate what's happening, kind of create a predictor of what the behavior is. So is this emergent? Has anyone been able to kind of guess what this logic is? Well, you don't have to guess. Let me just move to the next slide. What I've done now, and what it would be a good practice for you to do, is once you have kind of identified on a per line basis analytically what's happening in the assembly, see if you can't re-encode it into C code so that you can better isolate and understand what's happening in the logic between our input and what's being evaluated. So now let's re-examine what I just very arduously stepped through and reframe it and perhaps even composite it together to actually translate it into C instructions. And so what I'm going to do to make this readable so that you don't have to remember all the assembly instructions, I'm going to comment the assembly instructions out and pair them with my C code. So here we can see these were the first several sets of calls that we have very little control over, right? This is all the preamble stuff and the call to get those 6 numbers loaded into our kind of memory. So there's nothing that we can really do to kind of like define that part, right? That's none of our own work. Then the next thing we notice is, hey, there's actually a for loop that's going that starts at index 0 and increments until we hit 5. 0, 1, 2, 3, 4, 5. So, and we notice that our RBX value starts at 0 and we increment it each time until we hit that terminating condition at the very end. And so these are the logics here that reveal to me that that is a for loop in assembly. Okay, so once I have my for loop established, we had this line here where we were loading the effective memory address, we were advancing it by one address space. So this was, and then we were saving this. We were then loading the value into EAX. Well, that's the equivalent of moving into EAX, whatever the value in RBX is, plus 1. And RBX is the thing that we're incrementing across, right? 0, 1, 2, 3, 4. Then the next thing we're going to do here is in this instruction, we're going to use our base pointer, our offset, which is RBX, and our indexer, which is RBX, and then our offset, which is 4, because that's our data size. Well, that's the equivalent if I were to map that into array indexing terms. We would have this array where I'm using RBX as my index value, and this value here, this value here represents 0, so I'm not offsetting it at all. So I'm just indexing directly into that array space, and I'm adding that with the value that's in EAX. So that's like saying take EAX and add to it the value that's at this array space. And then we're going to override EAX with that new value. It's a destructive write because that's what the add operation does, right? It deposits in the accumulator register. Then we're going to do this comparison. And what our comparison, for ease of purpose, instead of checking, we're going to check to see if it's not equal and make the bomb explode, as opposed to checking if it does explode and like jumping past the bomb, right? In our logic, we're just going to invert that concept. So we're going to see if EAX is not equal to whatever the next index value is in our array. And so what that comparison looks like is we're taking EAX, and then we're going to index into the same array, but instead of looking at the current position where the leading value is at hexadecimal 0, we're going to look at that leading value where it's effectively offset in our memory address by 4 memory addresses. So that's like adding 1 to the data type. We're advancing 4 memory locations, which is 1 integer value, which is going to be the start of our next integer value in our array. And so if those are not equal, then we blow the bomb up. So there you go. So does everyone kind of see how we can map our assembly logic into a higher level language then? Very important skill if you want to do an analytical diagnosis of what's happening in this disassembled code. Okay, let's actually declutter this a little bit. Let's remove the assembly and just see what it looks like with the C code, because this, I think, will reveal the logic more so. Once we're happy with our translation, let's see if we can't flow with the logic. So here I have for RBX, no, don't want to do that. For RBX, starting at 0, and so long as RBX is less than 5, we'll increment RBX as our indexing value, as our loop control variable. We will increment RBX and set that to EAX. Then we'll take EAX and add it to whatever value it is we passed in. This array represents the 6 values we passed, and we'll override EAX with that. And then if EAX is not the same as the next value of our input, we'll explode the bomb. Now, what we have is something that we can solve algebraically. So suppose RBX is 0, right? We started at 0. That means that if array 0 plus 1 then has to equal array of index 1, right? So that means we're incrementing the next value in the sequence by 1. So then for RBX1, we're going to index into array 1, and then we're going to add 2 to it, because remember, this value that we're looking at is incrementing across this for loop. So we're getting this 1, 2, 3, 4, 5 value here for all 6 of our elements. So does everyone understand how this is generating our sequence? This is the algebraic terms that are generating our sequence. So if we assume that our array index is 1, starting with the simplest positive number, then we can then say that 1 plus 1 would then be 2 for the second term. Because remember, we don't have negative terms. And 2 plus 2 would equal 4. 4 plus 3 would equal 7, going by this. 7 plus 4 would equal 11, and 11 plus 5 would equal 16. So that means if we're right in our conversion and we did this algebraically, then our terms would be 1, 2, 4, 7, 11, and 16. So does that much make sense to everybody? Okay, so the analytical approach, let's see if this works. Okay, let's close this. Let's GDB our bomb. Let's set our breakpoint for explode bomb. Let's run with our solution so that we can skip past the first phase and immediately try this one. So what did we say? It was 1, 2, 4, 7, 11, 16. That's it. Okay, so that was just one way I can solve that. Now I want to show you a different way to solve the same problem. I want to show you the exploratory way that we might solve this problem as opposed to the analytical way. The analytical way is like, let's dump all of the assembly code. Let's evaluate it line by line. Let's understand what's happening with it. Let's follow the logic. Let's retranslate it into a higher level language. Let's algebraically solve it so that we can get a numerical sequence. And then let's use the debugger to see if that sequence is valid. Completely acceptable way. It's a lot of work though, right? A lot of time invested. This is also a way that is a lot of time invested, but it's a different way. So I'll leave it up to you which way you want to do it. We're going to do an exploratory way instead. Okay, let me quit out of this. Okay, so another way I can do this is let's launch our debugger. GDB. Perfect. And the next thing I'm going to do, I'm going to break on my explode bomb because I never want that to trigger. I always want to stop if that ever triggers. Now I'm going to set a breakpoint for phase 2. Bam. Okay, so now I have my phase 2. So now with my phase 2, we kind of cheated a little bit by being analytical. Do we want to do this in a dummy way? Because of time constraints, I'm going to have stated. Do I want to do that? Yeah, due to time constraints, because I have 15 minutes for this phase, I'm going to assume I already know that it is 6 digits that it has to be, right? Okay. Now, I could find out it's not by exploring as well, but in this instance, well, actually, let's not. Let's do this. Let's do this with hello world. Okay, so I'm going to do hello world. Oh wait, what am I doing? Oh, I'm still setting my breakpoints. Okay, so now I need to run. So let's run. Okay. Okay, so now let me give it hello world as the prompt. So at this point, I'm just finding out what kind of input do you want. I'm going to launch into here. Now I'm in breakpoint 2. And so just like when I use the debugger on the first phase, it's going to show me what is inside of this function. So here I'm at pushing RBP. So we know this is all like the preliminary stuff. So I might go to next instruction and then next instruction. And then let's do next instruction. Okay, and then what I can do here is at any time I can use disassemble to show me a more complete view of exactly what it is I can get my assembler dump. Let's step into, okay, we're already in, let me go to next instruction again. Uh-oh. I've got an unstable connection. I've lost my, okay, let's see. Has been closed because the server is taking too long. Okay, well, let's try to reconnect. Okay. Some technical difficulties because I'm reliant on a remote connection. Let's try that again. Well, let us go back here. Let's go back here. Let's go back to our bomb lab. Let's open terminal, ls. Okay. So let's go here to launch our GDB on our bomb. Perfect. Let us break on explode bomb. Let us break on phase 2. Perfect. Okay, now let us run with our phase solution file that completes through that first phase. Excellent. Okay, so we were saying, what if we just did hello world? Let's say we go in blindly and we're just poking and prodding in the debugger to explore what's happening as our code runs. So we'll go ahead and run that. We're inside phase 2. Let's go to the next instruction. Let's go into the next instruction. The first instruction I see that's kind of interesting. Is this call. Let's go into that instruction. And now can I step in this instruction? Let's see here. Okay, so now I'm in read 6 numbers. See how it now shows me where I'm at here? And if I look at so step I allows me to step into instruction, which then allows me to pass into another function, as opposed to next instruction. If I do next instruction, just keeps executing from the instruction that I'm in. So this lets me step in. Now I can use effectively disassemble dis-as to also see, well, what are the sets of instructions that are executed inside this helper function? So instead of having to use object dump, I can explore all this code and kind of watch as it's executing. So instead of passively reading it, I kind of have this ability to poke and prod at it. I can inspect my register spaces. I can have it walk line by line. And then here, I'll tell it to go to continue. I can see this is where it's doing this comparison here, and it's going to jump if it's greater to this, which is going to bring me to the return. And if it's not, it's going to jump. It's going to do. So I got to be greater than 5. So let me hit continue, and you see that brings me to explode bomb. So now all of a sudden, I know I call this read 6 digits, and now I know how many digits it is by just looking at that code. So now I can quit out of this because I don't want to explode my bomb. I can jump back in. I can set my breakpoints, break, explode bomb, and break on phase 2. Okay, so now I can start having some fun. So now I know, okay, it's got to be a set of digits. Let's do run. Okay, so suppose that I start with a -1. 0, 1, 2, 3, 4, right? That looks like 6 digits, right? What I can do at this point, okay, so let's go to next I. And let's go to next I. Let's go to next I. Go to next I. Uh-oh, unstable connection. Okay, so now we're going to call read 6 numbers. This is where we were dying last time because we didn't have any numbers to read. Let's see if we can make it through this. So now we're going to compare. And look, it tells me this jump is not taken. Well, that's a bad news for us, right? The reason why that's not taken is our number has to be great. It can't be negative. This is where we find out that condition. We've explored a little bit. We're like, oh, we need this jump. Otherwise, we're going to call this bomb. You see how bomb is the next thing? So if I go to the next side, what's going to happen? Yeah, it's going to, it's now notice I'm on the explode bomb. If I do next I, it's going to bring me into explode bomb. But at this point, I want to quit out. I don't want that. Okay, so now I know can't be a negative number. So let's do it again. Okay, so let us break on explode bomb. Let's break on phase 2. Now, keep in mind, we assume no knowledge so far up to this point. Everything we've learned by exploring what leads us to explode a bomb. And then reading at what jumps need to be taken at any given time to avoid that. And we're slowly kind of filtering out what's not the answer until we finally derive what will be the answer. So a lot of work, just in a different way. Okay, let us run with our phase solution 1.txt. Okay, so now let's suppose, okay, let's advance that so that it's 0, 1, 2, 3, 4, 5. Okay, we have 6 digits, right? Let's see where we go with this. Okay, so we're there. Let's go to next I. Let's go to next I. Now, really, next I. Now, actually, now that I look at this, this comparison is a pretty important one for us. This comparison with the D word, because that's going to determine if we explode the bomb or not. Actually, so let's actually set up a breakpoint so that we can actually prevent ourselves or see or stop when we get to that line. So we don't just need labels for breakpoints, we could use memory addresses as well. Okay, so actually let's quit out of this and do that. So let's set our breakpoint for explode. Let's set up our breakpoint for phase 2. Let us run psol1.txt. Okay, let us do 0, 1, 2, 3, 4, 5. Okay, let me do next I. Let me do a disassemble, actually. So I'm going to disassemble. The reason why I'm going to disassemble is I need the memory addresses. The only way I can get the memory address to get a breakpoint for a particular line is to do this. So the thing that I think is interesting that we want to stop at is going to be when we do this comparison here. So let me grab this memory address, copy that, and here I'm going to break. And to do a memory address, I have to lead with an asterisk. And then I'm going to paste. And now I have another breakpoint. Okay, so now let's do next instruction, next instruction, next instruction, next instruction. Ah, we just hit that breakpoint. Now, the lovely thing about this breakpoint is now we can inspect what's inside of our memory address. So what we can do is we can do info registers. This would actually give us all of our register space. That's a lot of noise. We don't care about all the registers. We're going to look at what we're comparing against, which is, oh, let me see some. Yeah, I did the wrong compare actually. So let us quit out of this and actually just relaunch. I want to do this at least once so you can see. So let's break on explode. Let's break on phase 2. Let us go ahead and run our our phase solution.txt. Let's do 0, 1, 2, 3, 4, 5. Let us actually get the actual one we want to check, which is going to be the compare that is right here. Yeah, this comparison to EAX, right? This is the one we want, because when because that's what's going to allow us, if that is equal, it allows us to jump to 51, which is going to avoid this explode bomb. This one, if you remember, is just checking to make sure we're not negative. We already solved that. So what we care about is this memory address here. So let me copy that one. Let me break on this. So now I'm going to start with an asterisk and I'm going to paste. Okay, so now that I have that set, I can now go to my next instruction. And now let's just let it execute next instruction. If I wanted to, I could just type continue and it will go to the next breakpoint as well. But I like being able to just step through so you can see line by line while this is happening. Yeah. Next I. Okay. Next I. Yeah. Next I. I'll just, okay. Continue. Okay. We're at breakpoint 3. So continue, we'll just keep going until I get to another breakpoint. So the application is done. So now I'm going to do info registers. Now this would actually display all the register information, or I can give it a particular address that I'm interested in. So here, I want to see what's in EAX that I'm comparing to. And remember, I'm looking for equality. That's value is 1. What did I put in? Well, if I want to see what I put in, I can use X and then 1 double word, because remember, an integer is a double word size, 4 bytes. And then I can actually then look up in the register space. So that would be RBP. I'll use my base pointer. And since these are registers, I got a prefix with a $sign. And then $RBX. That's my index value. And then I got to multiply it by my size of my data, by the scale of the data. And, oh, wait, what did I do here? Wrong direction. There we go. Oh, yeah, that's right. I put in a 0. So I'm comparing 0 to 1. Well, now I know the first digit. If they're equal, I jump. If they're not, then I die. So I need, okay, so to test this, let's quit out of this. Let's launch back into our debugger. Let's set our breakpoints. Explode bomb. Phase 2. Perfect. Let's run with psol1.txt. Perfect. Let's do 1, 2, 3, 4, 5, 6. We'll just keep with the increment. And just to see if this works, let's see if we can't get past that first number and get to where it says it's the second. And then you could see I would just keep doing this 6 times to get all 6 numbers without even having to know what the logic is, just knowing what the comparisons are at any given time. Hence the exploratory approach as opposed to the analytical approach. Okay, so at this point, let me do my disassemble so that I can get so that I can call my break when I do my compare. And that was here, right? So let me get this memory address. Let me copy that. Okay, let me set that break using an asterisk. And let me paste that. And hit enter. Okay, at this point, I'm going to tell it to continue until it hits that breakpoint. And so at this point, I'm going to say, okay, info registers EAX. So I got past the first one because it's not 1. So that means I'm now at the second digit where I'm comparing for 2, right? And if I hit continue again, yeah, next I. Oh, let's do continue. Where am I? I'm finally an explode bomb because I got the wrong value. So I'm out of time to show you how to do this all the way through, but you can see I take the same set of steps, and each time I find out what the next value is, and I iteratively do that until I find all 6 values. That's the exploratory approach of solving phase 2. Okay, with that, you should be able to solve the first 2 phases. Have a great spring break. We will reconvene next Monday. I'll publish the recordings probably tomorrow.